Okay, good morning or good afternoon everyone, and in this video lecture we would be covering the final topic for our midterm grading period, which is our acids and bases. So you might be already familiar with our acids and bases since you have some experience in the laboratory, but let's go about it on what acids and bases are and how it relates to pH. So we have two working definitions for acids and bases. We have our Bronsted-Lowry definition and we have our Lewis definition. We won't be going too much into the Lewis definition since it would be more useful in your organic chemistry. Instead, we're going to be focusing on our Bronsted-Lowry definition. So let's start with our Lewis acid definition so we could get it out of the way. When we say something is a Lewis acid, it's a substance that accepts an electron pair. So it accepts another electron so that a bond can form. For a Lewis base, it's the opposite. It donates an electron pair. So this is where the electrons are being obtained from. The donated electron pair is shared between the acid and the base and forms in a covalent bond. So this definition is actually one of the most flexible definitions since it can go beyond the traditional definitions of an acid and a base, as we might be familiar with more traditional acids and bases like our movement of hydrogen and our hydroxides. So we will be focusing this on the Lewis definitions on our organic chemistry instead. Next is the more useful one for our inorganic chemistry. We have our Bronsted-Lowry definition of an acid and a base. Acids and bases are described on how they interact with a proton. Now, please take note that for the Bronsted-Lowry acid definition of acids and bases, a proton is synonymous with hydrogen ion. Since hydrogen is 1-1, it's only made out of one proton, no neutrons, and one electron. When it gives off one electron and it becomes a hydrogen ion, it only has one proton in the structure, essentially making it so that hydrogen ion is a proton. So an acid is a substance that donates a proton, and a base is a substance that accepts a proton. Let's have an example so you could clearly see what we are talking about. So here on the screen, you would see an acid and a base. In our acid, it is our hydrochloric acid. So we're all familiar with hydrochloric acid. It is one of the stronger acids and it reacts with water. So in this situation, when hydrochloric acid reacts with water, since hydrochloric acid is an acid, it would give the hydrogen ion to our water. And in turn, it would form water, H2O, plus one more hydrogen. It would form our hydronium ion. What happens to hydrochloric acid when hydrogen leaves it is there would be a remnant of a chlorine anion. So in our case, hydrochloric acid acts as an acid and water acted as a base. Now this is the standard notation for an acid and a base. HA is our notation for acid. Please do not confuse A acid, B base, since it would more likely be confusing once we get to conjugate acids and conjugate bases. So for our definitions, whichever has an H, it is an acid. So when an acid reacts with a base would accept the hydrogen ion and our hydrochloric acid would give the hydrogen ion. Now we have names for the products. So a base that has accepted the hydrogen ion is called your conjugate acid. It is notated as BA. H. Base with a hydrogen ion acceptance, that is your conjugate acid. To remember, every molecule that has the H is an acid, while the remnant from your acid, the chloride, is your A negative or your conjugate base. Okay? Please remember these terms since this would be important, because later on we would be using that notation as a basis for our equilibrium expressions. So again, in this case, let's have another example. Here, our acid is water. So it's H2O plus a base, which is our ammonia. It would form, let's see. So H2O would give one hydrogen ion. So NH3 becomes NH4. It becomes your ammonium. And H2O minus H becomes OH. So H2O, since it gave off the acid, the hydrogen, it is your acid. Since ammonia accepted the hydrogen, it is your base. NH3, the base that accepted the hydrogen, became your conjugate acid, while water that lost hydrogen became your conjugate base. Let's assign the proper letters. Acid is A, HA. Base is B. Conjugate base means it's A negative, while your conjugate acid is your BH. Okay. So again, a conjugate acid is the base that received the proton. The conjugate base is the acid that lost the proton. And H3O is a form of water when it accepts a proton. So let's reiterate. Acid, HA. Base, B. Conjugate acid, BH. Conjugate base, A negative. Okay? Please be very familiar with the symbols since it would be used later. Okay, let's continue. So let's have a short review of our law of mass action. We have discussed this in our prior discussions in our equilibrium and our chemical reactions. But to simply have you recall, a general reaction has rates. So the rates of reaction is based on the concentrations of the reactants and the products together with the coefficients. So the general reaction is the rate forward is KF A raised to A times B raised to B. And the rate backward or rate reverse is KR C raised to C multiplied BD raised to D. So for this is only applicable for the equation AA plus BB is CC and DD, in which AA are our reactants, while our C and D are our products. Now going to continue with this one, we can, since this is a bidirectional reaction, it can reach equilibrium. So to recall, equilibrium is defined as this condition in which the rate forward is equal to the rate backward. Rate backward. For our equation, A plus B C plus D, and the rate forward is described as KF A B B, and our rate reverse is KR C sorry, this one D. If we combine the two constants together, KF over KR equals C D over A multiplied by B. This is your equilibrium expression. In which this can be converted to KEQ, since these are both constants, and this is our products and this is our reactants. So this could be concentration of products over reactants. Sorry for the illegible. I don't really have a table where I can place the pen tab. Okay, so this is our equilibrium expression. This would be useful in our acid and base equilibria. So this is 4 conditions in which bidirectional chemical reactions occur at a single system. There is a forward reaction and there is a backward reaction, and equilibrium is reached when the rate of the forward reaction is equivalent to the rate of the backward reaction. So to continue, acid-base equilibria can occur in solutions. So if you place an acid in water, it would have this equation on the screen. This is acetic acid, HAC. HAC, when placed in water, acetic acid would act as an acid and it would give hydrogen here. And this would form your hydronium, H3O. Acetic acid would have a remnant of your acetate here. And this would be your conjugate base. So our acid, HA, our base, B, our acid, which is our HB, this is your conjugate acid, or BH. And this is your conjugate base. Okay, please take a look on how acetic acid acted here. Acetic acid gave hydrogen to water, and that became our hydronium ion. Please take note that this is a reversible reaction, and when left alone, it would reach a state of equilibrium. Since it can reach a state of equilibrium, it can follow the equation for KEQ. So let's continue. KEQ is your products over reactants. So your KEQ would be your products, the products of your products. In this case, our reaction is HAC plus water is 2 H3O and our acetate. So our KEQ, let's have the products first. This is a balanced chemical equation. All the coefficients are 1, so we don't have to worry about that. So KEQ is equal to H3O, the concentration of H3O. Remember that if a chemical is in brackets, it is concentration in molarity. H3O multiplied by acetate, the concentration of acetate over acetic acid multiplied by the concentration of water. So this is the KEQ expression for our so this is the formula, or this is the equilibrium expression for our KEQ of acetic acid in water and when it reaches equilibrium. So acetic acid, when placed in water, it would ionize into hydronium ions and to our acetate ions. Now, an interesting thing here is the concentration of water. For dilute solutions, usually reserved for measuring acids and bases, the concentration of water is constant. We know that the concentration of pure water is 55.4 molarity or 55.4 moles per liter. To obtain this, all you need to do is to get 1 liter of water. Since 1 liter of water is 1 kilogram of water, and that is 1,000 grams. 1,000 grams of water in 1 liter of solution, that is a liter of water. Since we know the molecular weight of water, 18 grams of water is 1 mole, you'll obtain 55.4 moles per liter. So that is the concentration of pure water. Since we know the concentration of pure water, this can now act as another constant. So since the value of H2O never changes, since it's a constant, we could multiply it with our KEQ. Since KEQ is a constant, water is a constant, you could now have a new constant. That is your Ka. And that Ka is described or is defined as ionization constant of an acid. Since acetic acid ionized to hydronium and acetate, this is the equation for that ionization. So Ka is equal to H3O and concentration of acetate over the concentration of acetic acid. Now this is specific for acetic acid. Let's make it more general. Okay, so let's rewrite Ka. H3O is our conjugate acid. So that is our BH. AC or acetate is our conjugate base. And our acetic acid is our acid, that is our HA. So to obtain the Ka of an acid, this is the formula you would be using. So Ka describes the strength of an acid. Since the higher the Ka of your substance, the more hydrogen ions it can produce. And the hydrogen ion it produces is usually hydronium if it is an aqueous solution. So Ka is the ionization constant of an acid. It is described as how strong your acid is. It is and the strength of an acid is described on how much hydrogen ions can be produced when it dissociates in water. So if you have a strong acid, it dissociates into more hydrogen ions. If you have a weak acid, it dissociates into less hydrogen ions when exposed to water. Okay, so that is our Ka. Let's continue. Okay, so one problem with Ka is the value of Ka is low. I mean, it's usually an exponential number raised to a negative value. So for convenience, it could be easier to grasp in concept, Ka values aren't used that much. We could use it in the form of pKa. So pKa converts that very small number into a more manageable number. So pKa Okay, so to get pKa, you need to get the negative logarithm of the concentration of your Ka. Sorry. You don't place it in brackets since it's not the concentration. Okay, negative log Ka is our pKa. So pKa would give you a number like around 1 to 11 usually. Now, pKa could be back converted to Ka if needed. To get Ka from pKa, all you need to do is to apply log raised to negative Ka. This would negative pKa. This would result to your Ka. If ever you need to back convert to your Ka. So in pharmacy, we usually use pKa values. So a strong acid has a small pKa value around 1 to 3, and a weak acid has a large pKa of around 8 onwards. Now, it is a good system since it is synonymous with our pH scale, in which our pH scale is the lower the number, the more acidic it is, and the higher the number, the more basic a substance is. These are the relative strengths of some common acids and their conjugate bases. So these are expressed in pKa values. Next, we have the uniqueness of water. So water is unique since it can act as either as an acid or as a base. If you recall the earlier equation, hydrochloric acid plus water forms hydronium and chloride, and water plus ammonia forms hydroxide and ammonium. In the first equation, hydrochloric acid gave water a hydrogen ion. In this case, water acted as a base since it accepted the hydrogen ion. In the second equation, water gave ammonia a hydrogen ion. So in this case, water acted as an acid. What this means is that since water can act as both an acid and a base, water can react with itself. It's called your auto-ionization of water. It's called your auto-ionization. Meaning water, when left alone, it would ionize to its constituents. So let's have an equation of water. So let's have 2 moles of water. H2O plus H2O. Let's have 1 molecule of water act as an acid. So it's going to give off a hydrogen ion. So the product would be hydronium. H2O plus another H, hydronium. And since H2O left or gave off 1 hydrogen, it became hydroxide. Okay, so this is the dissociation of water molecules. 2 moles of water will break into hydronium and hydroxide. And since this is an reversible chemical reaction, it can be expressed as an equilibrium reaction. So Kf over Kr equals products over reactants. Our products is H3O and OH. Our reactants is 2H2O. Now this one is equivalent to KEQ. So let's rewrite it as KEQ instead. Now, earlier in our discussion of acids, we said that water can, water's concentration is constant. It's constant at 55.4, meaning this is constant, this is constant. We can move it to the side with constants. So KEQ times water equals H3O and OH. These are all constants. H2O, H2O, KEQ, these are all constants. We can convert this into a new constant. That is KW. KW is the ionization constant of water. And KEQ is equal to H3O and OH, the concentration of H3O and OH. Now, the interesting thing about KW is KW has a value of 1 times 10 to the negative 14. And pure water at 25 degrees Celsius, H3O and OH are equimolar, meaning they have the same amounts. And that amount is 1 times 10 to the negative 7 moles per liter. And OH is also 1 times 10 to the negative 7 moles per liter, or molarity. Now, the ionization constant for water is interesting because when you multiply the concentration of hydronium and hydroxide, you would always get 1 times 10 to the negative 14. Now, we could use this equation to describe acidity of a substance. Our standard way of describing acidity of a substance is pH. Okay. Now, this hydronium is your hydrogen ion concentration. This is your hydroxide ion concentration. Now, pH describes how acidic a substance is by counting how many hydrogen ions there are. The problem with this one is it's a very small number. 1 times 10 to the negative 7 is a very small number. Hence, if we can do the same with pKa, in which we applied negative log to Ka to make it more manageable, we could also apply negative log to everything here. So the negative log of hydrogen ion is equal to pH. Similar to how we applied negative log Ka became pKa. And when we apply negative log OH, it becomes POH. We use pH conventionally. And the cool thing about pH is it describes the acidity of a substance. This is the basis of our pH scale. Our pH scale runs from 0 to 14, in which 0 is the most acidic, and 14 is the most basic. Please take note, you can also make a POH scale, but it is uncommon. We tend to use pH instead. So when a substance is more acidic, it has more hydrogen ions and it has a lower pH. If it has lesser hydrogen ion concentration, it has a higher pH, meaning it is more basic. Okay? Now, another interesting thing is whenever you add pH and POH, it always ends up with 14. because if you apply negative log Kw, it is 14. So 14 equals pH plus pOH. These are the useful equations you should copy. So boxed here are the most important equations you should copy. Okay, so let's recap. We are now familiar with acids and bases. In terms of Bronsted-Lowry definition of an acid and a base, an acid gives off hydrogen, while a base accepts hydrogen. An acid or a base, when placed in water, it would ionize. And in terms of an acid ionizing, it is it would give you an ionization constant of Ka. The ionization constant Ka describes how strong an acid is. And since Ka is a very small number, we tend to apply negative log to make it a more manageable number, pKa. pKa describes the strength of an acid. The higher it is, the weaker an acid is, and the higher it is, and the lower it is, the more stronger your acid is. Similar to pH, in which if you have a low pH, you have an acidic substance. If you have a high pH, you have a basic substance. We also talked about how water can ionize and how we can describe the ionization of water and how the pH scale was formulated. So on the screen you would see how pH was derived. Okay, so that would be the conclusion of our lecture. Please do copy the formulas, and sample problems would be given for you to practice on. The most important ones is how to compute for Ka, pKa, pH, pOH, and concentration of H and OH. Side note, H3O is equal to H. That is the same. Okay, that would be all. Thank you for listening, and if you have any questions, you could comment down in the comment box and I'll do my best to answer them. Okay, that would be all. Thank you.